Hey everyone, and welcome to this explainer. Today, we're diving straight into the fascinating everyday physics that are constantly happening all around us. I like to think of physics not just as dry equations on a chalkboard, but as the actual hidden magic that runs our physical world. Today, we're going to master the magic of invisible forces, specifically the really incredible phenomena of pressure and buoyancy. We're going to break down exactly how these forces work, why they actually matter, and how they let us pull off massive, mind-blowing feats of engineering. Seriously, by the end of this explainer, you are going to look at the world around you in a completely different way.
So, let me just ask you right off the bat, do you feel the pressure? Right now. Take a deep breath in. Well, right at this very exact moment, there's an invisible weight of the entire world pressing down on you from all sides. Crazy, right? You probably don't feel it consciously because you're so incredibly used to it, but it's always there, pulling the strings and dictating how fluids and gases interact with practically everything. But before we get too deep into the actual physics, let's nail down exactly what kind of pressure we're talking about today.
To set the stage, let's distinguish between two totally different types of pressure. There's an old physics joke that perfectly hits the nail on the head. Peer pressure means they don't like you enough. But gas and water pressure? Yeah, they don't like you at all. While peer pressure is this psychological weight we all deal with, physical pressure is a literal, relentless physical weight pushing against you 24/7. Okay, so let's dive into this and define what physical pressure actually is in scientific terms.
All right, so the absolute crucial starting point is our fundamental definition. Pressure, which we represent with the letter P, is simply the force, or F, that is exerted per unit of area, or A. Basically, think of it as a concentration of force. If you take a certain amount of force and spread it out over a really large area, the pressure is pretty low. But if you take that exact same force and concentrate it down onto a tiny microscopic pinpoint area, boom, the pressure becomes insanely high. To put that into perspective, our standard unit for force is newtons, and for area, it's square meters. So that means our official unit for pressure is newtons per square meter, which is also known as pascals.
Let's actually test this concept out. Imagine three identical, solid, magical triangular vessels, each weighing exactly 100 kilograms. Which one casts the heaviest spell, or in our terms, exerts the most pressure on the ground? Say the first one has its widest face flat on the ground, covering an area of 100 square centimeters. The middle one is resting on a smaller 10 square centimeter face. And the last one? It's perfectly balanced on its absolute tip, resting on an area of just one single square centimeter. Because the downward force, their 100 kilogram weight, is exactly the same for all three, that vessel, balanced on its tip, is exerting massively more pressure on the ground. It's all about how tightly you concentrate that force.
Now let's see how this whole concept shifts when we take a plunge underwater. We can actually transform our basic solid pressure formula into a highly specific formula just for liquids. It's like a 5-step recipe. Step 1, we start with that original formula, pressure equals force over area. Step 2, in a fluid, the force is simply the weight of the fluid sitting above it. Step 3, we know weight relates to mass, and mass equals density times volume. Step 4, well, what's the volume of that fluid? It's just the area multiplied by the height, or the depth, of the liquid. And finally, Step 5, when you plug all of that back into your original fraction, the area on the top and the area on the bottom literally just cancel each other out completely. And what we are left with after all that canceling is this beautiful, super elegant formula for liquid pressure. P equals h times rho times g. In plain English, that translates to pressure equals the height or depth of the liquid multiplied by the density of the liquid multiplied by the acceleration due to gravity. Did you notice what is entirely missing from that whole equation? Area. The area is gone. In the realm of liquids, the shape or area of the container doesn't matter at all. The pressure, which is acting in all directions simultaneously, depends solely on how deep you go, how dense the fluid is, and gravity. That's it! And hey, this isn't just some abstract theory. It's exactly how we solve massive, practical engineering mysteries. Let's look at a real-world riddle. Imagine you're looking at a giant dam holding back a vast, sprawling reservoir of water. The maximum pressure at the very base of this dam is a whopping 750 kilopascals. Now, because we know the density of water is exactly 1,000 kilograms per cubic meter, and gravity is a constant, we can use our shiny new formula to easily calculate exactly how deep that water is. Engineers use this exact principle to ensure dams are built thickest at the very bottom, just to withstand that immense, depth-driven pressure.
Okay, now let's float up out of the water and straight into the sky. We've totally conquered liquid pressure, but what about the air we breathe?
Well, according to the kinetic theory of gases, gas molecules are these incredibly tiny things spread really far apart, and they are in a state of constant, rapid motion. So gas pressure is simply the result of millions and millions of these invisible particles relentlessly bouncing off everything around them in perfectly elastic collisions. It's basically a microscopic, never-ending game of bumper cars. And these frantic collisions are governed by a few really fundamental rules that you absolutely need to know. First up is Boyle's law. Boyle's law tells us that if you shrink the space these gas particles are in, well, they end up hitting the walls way more often, which drives the pressure up. Simple enough, right? Then we have Gay-Lussac's law, which explains that if you heat that gas up, the particles get energized, they move faster, and they hit harder, which, again, spikes the pressure. And what if you want to keep the pressure completely constant while heating them? Well, Charles' law dictates that the volume must expand to give those super energetic particles more room to fly around. So, bringing it all back to our atmosphere, the pressure at sea level is exactly 1 atmosphere, and as you climb up a mountain, there's literally less air above you, so that pressure naturally decreases.
And this brings us to a really brilliant way we actually measure that chaotic, invisible bouncing gas. Enter the Mercury Barometer. I mean, it kind of looks like a magic trick, but it is pure, elegant physics. Picture a glass tube filled with mercury sitting inverted in a little dish. The atmospheric pressure, all those tiny air molecules we just talked about, pushes down on the pool of mercury in the dish, which in turn forces the mercury straight up into the vacuum of the tube. At normal sea level pressure, the atmosphere is strong enough to hold up exactly a 0.76 meter or 76 centimeter column of mercury. If the air pressure outside goes up, it pushes that column even higher.
But let's be totally honest here. Carrying around a long, fragile glass tube full of hazardous liquid mercury isn't exactly practical or, safe. And that is exactly why we use something called a manometer for day-to-day measurements of gas pressure. It's essentially this U-shaped tube containing a safe liquid like water, though sometimes they do use mercury. When one end is hooked up to a gas supply, the pressure of that gas pushes the liquid down on one side of the U and up on the other. By just measuring the difference in the liquid's height between the two sides, we can calculate the exact pressure of that gas. So much easier.
Now, I know manometer problems can look incredibly tricky at first glance, but there is actually a highly structured, pretty much foolproof 4-step checklist for mastering them every single time. Step 1. Draw horizontal equal pressure lines across the U-tube. Remember, pressure is only the exact same horizontally when you're in the same continuous fluid. Step 2. Draw arrows showing the direction of the force caused by the weight of the fluids pressing down on those lines. Step 3. Write out your relevant equations, keeping in mind our trusty P equals h.rho.g formula from earlier. And finally, Step 4. Simply solve the equation. I promise you, if you follow these 4 steps, literally no manometer riddle is going to stump you.
All right, now we are perfectly primed to introduce our first master of fluids, the legendary Blaise Pascal. Pascal's principle is a total game changer. It states that pressure applied to an enclosed liquid is transmitted equally without any loss to every single part of that liquid. Think back to our formula. Pressure is force over area. If the pressure has to stay constant everywhere throughout the fluid, then F1 over A1 absolutely must equal F2 over A2. This seemingly simple realization, it is literally one of the most powerful foundational concepts in all of modern engineering. Let's look at how Pascal's principle acts almost like a magic wand, magically turning a tiny little force into massive, heavy lifting power. Imagine a standard hydraulic system. On the left side, you've got a small piston with a very small surface area. On the right, there's a large piston with a huge surface area. If you apply a really small force, say just 40 newtons, to that small piston on the left, that resulting pressure is transmitted equally all the way through the fluid. Because the piston on the right has a much larger area, the fluid ends up exerting a proportionately massive upward force on it. This is the exact reason why pressing lightly on the brakes in your car stops a speeding vehicle, and how a tiny pump at the mechanic's shop can lift a 2-ton truck straight up into the air. No magic, just Pascal.
And that brings our journey to our second master of fluids, the great Archimedes. Archimedes' principle finally solves the age-old mystery of why things float. He figured out that when an object is completely or even partially submerged in a fluid, it experiences this invisible upward reaction force. And the real magic of this principle is that this upward buoyant force is exactly, perfectly equal to the weight of the fluid that the object displaces or pushes out of its way. To make this instantly relatable to your own body, I want you to think about sitting halfway on a chair, using your legs to support the rest of your body weight.
You are actively pushing down on the chair, right? But the chair is also pushing right back up on you. The exact same thing goes for fluids. The fluid is pushing back on you exactly as much as you push into it. If you just dip your toe in the pool, the water only pushes back on your toe. But if you jump in and submerge your whole body, you're displacing so much more water, and that water pushes back on all of you, creating this massive, buoyant force that makes you feel wonderfully weightless.
So, to wrap things up, I want to end our explainer with a lingering thought experiment. Let's test your brand new mastery of the magic of physics. We know an object only floats on water if its upward buoyant force matches its downward weight. But can you design a closed cylindrical submarine made of solid mild steel, which has a massive density of 7850 kilograms per cubic meter, that perfectly floats in seawater, which only has a density of 1027 kilograms per cubic meter, without it sinking like a rock to the bottom or popping up to the surface? To achieve this perfect state of neutral buoyancy, you'd have to precisely balance the massive density of the steel with just the right amount of hollow volume inside, ensuring the overall average density perfectly matches the ocean water around it. I'll leave you to ponder that incredible engineering marvel. Thanks so much for joining me on this journey through invisible forces.